What's a limit? In basic calculus, we can use limits to analyze function behaviors, and more importantly, to define the derivative. What does it actually mean when it says x right arrow a here? First, the arrow means approaching. So x right arrow 2 means x is approaching 2. One way to think of it is to look at a sequence of numbers. We can pick a starting point 2.5, then 2.1, then 2.05, then 2.01, and so on. When do we stop? We don't stop. But that's not the only way we approach 2. We can start at something on the smaller side of 2, say 1.5, then 1.9, then 1.95, then 1.99, and keep going. By using this idea, we can look at a function's behavior as x approaches 2. For the ease of calculation, I picked this function. Yes, this is easy calculation. We can generate two tables like this, and we look at the trend of the function values, and we could see that it looks like the function is approaching 4, so we say the limit is probably 4. We had just observed that f gets closer and stays close to 4 as x gets closer to 2. Symbolically, we can write that out like this. So limits can possibly be calculated numerically, and using computers will be a good idea because they are good at generating tables like these. Well, that's not the only way that we can find this limit. If you like drawing, we can try a graphical approach. But hey, computers are also good at graphing functions, and usually better than we are. True, but we can definitely graph this one. Remember, I picked an easy function? It's easy because we can factor the top and cancel x minus 2. Haha, do you see that we are only graphing x plus 2, which is a line with a hole because we can't allow x to be 2. Plotting all those points listed in the tables, we can see all those dots are getting closer to the hole. They really remind me of ant trails. Yes, ants probably know calculus if you give them food. From that graphical approach, we observe that the limit of f is the same as the limit of x plus 2. It turns out that it doesn't matter whether there is a hole on the graph since x approaches 2, x is not equal to 2. So this gives us the algebraic approach for computing limits. Here we have the intuitive definition of limit. So far we have seen 3 approaches of computing limits: numerically, graphically, and algebraically. We now look at one more example in which we attempt to find the limit numerically. This will raise a red flag of always finding limits using the numerical approach. Approaching 0 from 2 sides, we have this table of function values. At this point, it feels like we are pretty close to 0, so we guess the limit may be -1. However, going smaller, we realize something bad happens. The function value is not even close to -1. Switching to the graphical approach, we can see near 0, the function oscillates between -1 and 1 without stopping at a value. In other words, f does not approach a single number L, so the limit does not exist. This is a pitfall of the numerical approach of finding limits. We do not know when we can stop as we pick values of x approach a. There are more to limits. We'll continue next time. Subscribe to stay tuned. See ya.